Hello. All right. So we are indeed polyfilling video in WebAssembly, which is kind of crazy, but it does work and turns out to actually be useful sometimes. So first, I'm going to start with a brief history of video support in Wikipedia, which explains why we use WebAssembly for video playback in some browsers, before I get into how it works and how it performs and how that's changed over the years and is soon changing even for the better. Imagine a dark time when dinosaurs ruled the earth, before there was a video element in HTML. This was the early days of Wikipedia. You could not just put a video on the internet and expect it to work back then. These were indeed dark times. However, they were good times because you could do all kinds of fun things. But you couldn't do everything. That's okay. We, in particular, at Wikipedia, had very strict rules about using open source software in our production environment and open formats and data formats for everything that we produce and consume directly. In part, this is to ensure that everyone who wants or needs to can replicate all the information in Wikipedia with no additional rules or license restrictions beyond continuing to keep it open in a share-alike style license. Now, that did end up having some complications. Even in the early days, we had file formats that were very commonly used on the internet, such as GIF files. Some of you may remember that there were actually patents claimed on the GIF compression format for some number of years, and we weren't actually able at the time, at least under our interpretation of our format rules, to use those files. So we instead recommended people use ping images, which are in many ways more advantageous, although when the patent ran out in 2003 and 2004, we went ahead and added support. Similarly, we didn't touch MP3 audio for many years until the patents ran out in 2017, instead using the open ogg Vorbis and FLAC and other formats that are fully open and have no patent restrictions on them. And we're only just adding MPEG-1 and MPEG-2 support. You might say we're a little behind on some things. Now, back in the day, when Opera first proposed the video element for HTML, they were proposing the ogv codec, which many people don't remember anymore because it's mostly been obsoleted by WebM's VP8 and VP9. But back in the day, it was the only freely available codec available with a patent license that allowed anyone to use it with no restrictions. There were weird little licenses that you had to get for just about everything else. And as the standardization process moved along, it became clear that the browser makers couldn't all agree on using that format. Either it wasn't technically good enough, or there was a risk of submarine patents, or et cetera, et cetera. The primary alternative that was recommended was H.264, which is very commonly found in MP4 files all around the internet. And it's a pretty good format, but it has a patent license requirement that doesn't expire until 2028, I believe. So it turned out to be problematic for distribution of open source software that would use a decoder or encoder. And in particular for Mozilla, this was a big complication for a number of years. And it took a while for all the browsers to agree on a de facto format, even if they didn't have a common format. However, with our strict open file format policies, we were never quite able to agree on it. So this left us, as early adopters of ogv and the video element, working in Firefox and Chrome and Opera and several other browsers, but not working in Internet Explorer and Safari, which didn't adopt ogv or WebM. We originally used a Java applet as a fallback back in the day. Java applets were, well, they were interesting. And they sort of worked, and they sort of did a lot of the things that WebAssembly does today, but with a much heavier runtime in a day when computers were not as fast. So this was not necessarily the greatest thing. In addition, there was simply the fact that over time, Java applets and other plugins simply became less appreciated by the browser makers due to compatibility issues, security issues, et cetera, over time, and those were phased out. So this eventually left us with no fallback, and it was necessary to go looking for something else. And are we working? We are not working. That's okay. I have another button. Oh, I'm on the wrong window. Ta-da. So, we actually had a community consultation at one point as to whether to adopt H.264, and it didn't go well, but that's okay, because we have workarounds. We play the long game at Wikipedia. If a file format isn't okay now, it's going to be okay in a few years. We'll use it then. And it turns out that you can get around things. So, RIP Java. Java applets no longer okay, plugins no longer okay. What were our options? Around 2013, 2014, I started doing some research on what we could do as an alternative, working within the constraints we had of the file formats. I found a Vorbis decoder written in Flash that was very interesting and did audio only. One thing that I really didn't want to do was to replicate the entire codecs in JavaScript or Flash. That sounded like a huge bunch of development work I didn't want to do. In our Java applet, that had already been done by someone else, which was an impressive feat. I'm very impressed that it worked at all, but I really didn't want to have to maintain those in additional libraries. Taking a cross-compiler that can take our existing C code for a standard codec and just create your Flash or JavaScript, well, that would be a lot nicer, wouldn't it? Well, it turned out that there were a couple of possibilities. One thing that I found was the cross-bridge compiler for Flash, which was pretty cool in its day. But it was very difficult to maintain, I found, and very difficult to debug using the free tools that were available to me at the time. However, it did actually perform pretty well compared to contemporaneous browsers. However, it was much more fun when I found emscripten. I found another project decoding Vorbis in JavaScript, which used the standard C library compiled to JavaScript with emscripten, and performance was pretty good. It was good enough in Safari. It was good enough even in IE for relatively modest files, and I was able to adapt it to video without a whole lot of trouble. And it was all a lot easier to debug than Flash. Emscripten also seemed to have a lot of developer momentum behind it, which I can certainly see by the last few years was the right call to make. So I minimized our usage of Flash to just an audio shim for IE. Although the cross-bridge compiler performed well in terms of the actual code logic, it simply was too hard to use. So bare minimum of Flash. In Safari and other browsers, we didn't need any Flash at all because web audio was available. Now, as a fun aside, I also wrote recently a Wasm to Swift compiler, which takes a WebAssembly module and compiles it into a Flash ActionScript bytecode file. It's not necessarily a useful project, considering especially that the Flash plugin is set to be decommissioned at the end of this year and will no longer exist in any browser, including Internet Explorer 11. But this was mainly to check whether my old assumptions still held. And indeed, I found in benchmark testing that the codecs in Flash were about 1.5 to 2 times the speed of Internet Explorer 11, which, would have been pretty good if I had had this tool several years ago, but they're still about 4 times slower than WebAssembly in modern native browsers. So I'm not going to invest too much more time in that. So what we ended up putting together was called ogv.js, and it's a video player that emulates the video element API, written primarily in JavaScript for the front end with emscripten modules for the codecs and demuxers. Work is split between a main thread where we're doing network I/O, We run the demuxer, which has to do a lot of back and forth to the network buffering. And we do the actual canvas drawing with WebGL if available, and the web audio or flash audio output. And then the codecs themselves are run in separate workers, which allows us to do a bare minimum of threading back in the olden days before you had WebAssembly threading and shared memory buffers available. So the video codec was able to run as long as it needed to on a background thread, as long as it was able to run in time to output each frame. Now, a performance journey in 3 acts. First of all, what is performance? Well, there's a lot of interesting ways we could measure performance, but we're going to stick with the simple, which is the ratio between how fast your native code runs, or the fastest code you can get to run, and the slowest code you can get to run. Since we're taking the same code from a C library that already exists and just transforming it to other formats. And it's been an amazing journey over the past few years. Act 1, from JavaScript to WebAssembly. So back in the day, emscripten did not have WebAssembly. It produced JavaScript directly. And this turns out to kind of suck in some ways. It's amazing that it works. And it does work pretty well, but you have to jump through a lot of hoops. For instance, JavaScript has no integer addition operator. It has a floating point addition operator. And if you add 2 integers, they can overflow the value of an integer. So if you really want integer addition, which you probably do if you're compiling C code, you have to coerce that result over to a integer by using a bitwise operation such as OR 0. Now, that operation is reasonably simple to do, and it turns out that it can be optimized really well in the browsers once they know about it. But it's still not great, and it means that if you're in an old browser, you don't have great performance. If you're doing multiplication, which it turns out happens a lot in video decoding, it's even worse, because if you overflow again, you have an even more complex thing. So we have this little math.imul function, which was actually added to ECMAScript specifically because of emscripten and other compilers targeting JavaScript as a language. Because having to do polyfill it with this fun little function is incredibly slow. So you don't want that. Additionally, memory access in JavaScript turned out to be kind of slow. There's 2 main things that you do that slow it down. The first is that typed arrays require a length check on every access. You don't want to go beyond the bounds of the array. That's okay. But it does mean that everything gets slowed down. Additionally, you have to downshift the addresses from a full address space to the address space of the size of the integer. So for instance, for a 32-bit integer, you have to downshift it by 2 bits to divide by 4. And if you're doing unaligned accesses, that will end up giving you a wrong result. So you have to expand it into separate byte loads. All this stuff really slows down your code. Now, there was the ASM.js subset of JavaScript, and with validation in some browsers, especially Firefox and some others, you could optimize a bunch of that stuff away really fast. And in fact, it performed really well. So well that it led to the creation of WebAssembly, which is even better, which we'll get to very shortly. But if you're deploying your JavaScript builds to Internet Explorer, you don't get any of those benefits, which is good. No, it's not. It's bad. Which is bad unless you don't care about Internet Explorer 11, which a lot of people don't, but we still do because we like equity of access. So that's a good idea. But with those optimizations, you end up with about 4 times faster performance, which makes a big deal. Now, let's see if I can get this demo to work. Hello, demo. All right. So here's Internet Explorer running a JavaScript build of ogv.js, and let's see how it runs. Now, this is a relatively modest 360p resolution. And you'll see it kind of runs,
when
but
people look at it,
it's a little choppy. And that's not really good because this is a really fast
it's a
computer.
very natural thing.
And most people who are running Internet Explorer are going to be running really slow computers. So IE is not the best experience still. But if we pull up that same file over in one of these is Safari, even with the JavaScript backend, oops, it should play. Let's reload it. There we go. It's much, much smoother at the same resolution.
When people look at it,
And you can see from this performance graph down at the bottom,
crazy. That's a very natural thing.
our CPU times are much, much lower here than they are over here.
It is the result
And in fact, that 4 times difference means we can pop up a couple of resolutions. And let's try 720.
of reasoned engineering.
All right, that still runs pretty good.
But it's
Now, here comes WebAssembly. It's time to go fast. All right. So let's switch over back to WebAssembly.
still looks crazy.
Same resolution, 720.
The top of the app.
Our graphs
Down
here
the
are even
surface.
lower. It ends up being about
It takes
twice
us
as
7
fast
minutes.
in Safari to run the fully optimized WebAssembly versus the optimized JavaScript. That's pretty good. That's given us a 8 times performance increase from Internet Explorer 11 era browsers to modern WebAssembly browsers. Oops. But what is next? Act 2, threading across multiple CPU cores. Now, almost every CPU these days has multiple CPU cores. If you have a smartphone, it probably has at least 2 cores. It probably has 4 cores. It might have 6 or 8 cores. Your laptop probably has 2 or 4. And of course, a big workstation or server is going to have a bajillion. So you want to be able to make use of those CPU cores if you can. Everything that we were showing in a demo before was running on a single CPU, even though this is a 6-core machine. So that's pretty much a waste of all of your hardware, which is not fun. You don't want to, have 8 cores and just get the benefit of 1. So there are threaded builds as well. This is still a little bit experimental. I haven't deployed it, in part because it's not available yet in Safari, but it works fantastically in Chrome, and we're very much looking forward to WebAssembly threading coming to Safari as our target environment. So in the threaded build, it's slightly different from the single-threaded build because we can have multiple workers for the video codec. It's using the pthreads API, which means that we're able to use the existing threading support in the libvpx codec library and in the David codec library for AV1 without having to rewrite a whole bunch of manual threading stuff, which would have been necessary if we had some weird non-standard API. So that's pretty cool. Now, browser support is still incomplete. It's mainly Chrome that has things released. Firefox is coming soon. There will be some requirement to use these new cross-origin opener policy and cross-origin embedder policy and other funky new headers, which is primarily to ensure that sites are opting in to the use of shared memory. The theory is that browser implementations that do not fully separate multiple sites from each other in separate processes, if they simply allow shared memory directly, it could allow for some exfiltration attacks. So you want to make sure that only safe environments are used. So that will be a slight difficulty to deployment, but it is relatively straightforward if you're running an application. It is slightly more complicated if you are running a library that is used within an application that has HTML pages you don't control yourself. So we'll see how all that comes out. Now, there's a couple other gotchas in WebAssembly threading with emscripten. The first is that launching pthreads directly from the main thread on the web is slightly difficult because it actually requires a run back through the event loop to fully create a new thread from a web worker. It turns out that a lot of code does not work very well within that constraint, but as a workaround, there is a pre-launch ability to pre-allocate a couple of workers. What we do for ogv.js is to pre-allocate one worker, which then launches additional workers as needed. So this works relatively straightforwardly. The other weird thing that I noticed is that some operating systems, such as macOS, at least on some processors, will introduce specter mitigations that disable hyperthreading in some applications, including in the browser. So from that little performance graph up there, you can see that only every other processor is engaged, which is, sounds like a waste of processor time, but it's only a slight waste of processor time because those aren't entire cores. Those are just the hyperthreading cores. And you would only get like a few % improvement from fully occupying both sets of hyperthreading cores. Still, losing that performance is kind of sad, and I wish I could get it back. Act 3, single instruction, multiple data. Now, SIMD operations, also known as vector ops, are another hidden performance gem in your CPU. Every CPU out there today in common web browsing capable hardware has some sort of SIMD extensions available in it. And that's good, because that means we can use it. Now, if you look at the whole wide world of CPUs, there's a variety of different vector lengths. Pretty much everything supports 128-bit vectors. Some support 256-bit vectors. Some support 512-bit vectors, but those are pretty rare, and you have to have a high-end CPU for that. So because we're hitting the sweet spot, the WebAssembly SIMD extension only specifically targets 128-bit vectors because it's supported on Intel, it's supported on ARM, it's supported on MIPS, it's supported on PowerPC. Anything you can think of, you can end up doing most of these operations pretty efficiently. Now, the fun thing that makes these extra interesting is that the whole point is you're issuing a single instruction that does operations on multiple pieces of data. So you break down that vector into, say, 2 64-bit chunks, or 8 16-bit chunks, or 16 8-bit chunks, or whatever, and you perform operations on all those separate lanes individually at the same time. Which in theory can give you a pretty linear scale up for particular algorithms. It generally won't improve your entire code base because it's only going to help with specific bits that are easily parallelizable. And very often you will have to write manual code to get a good benefit. Sometimes you can get really good results from the LLVM auto-vectorizer, but I found it didn't help at all on the video codecs, and I definitely had to write my own code. So when you're working with WebAssembly in emscripten with C and C++ code, there is a header file available called wasm_simd128.h, which defines a v128t type for the vectors, and a whole bunch of functions which represent all the intrinsic operations that you can perform on the vectors in various sizes, which means that you can run those directly. Now, there is sometimes a surprise when you do this, because you might write very specific instructions, and then when you go and look at your disassembly, you actually got different instructions. This is because the compiler and the optimization passes sometimes decide, you know, that instruction was good, but this other instruction should be slightly faster. And it may or may not actually be faster, but it will give you the same result. And hopefully it actually is. One more thing on those vector ops. The big advantage of using C and C++ and those vector functions instead of writing everything in manual WebAssembly text format is that you get the benefit of composability. You can write inline functions, you can write macros, whatever, that are very small little functions, and then you throw them all together and it compiles it into one big giant chain of stuff that would be a lot harder to maintain manually. So here's an example, one of the filtering functions in libvpx's VP9 decoder called convolvert. It appears in a couple of other functions that are at the top of the profiling graph, so they're pretty good candidates for accelerating with SIMD. Now let's just look at the middle part of it. You can see there's a big loop that loops over several pixels in the X direction, then it loops over in the Y direction, it grabs some source data, or rather it pulls a pointer for some source data, grabs a set of filters suitable for the coordinates it's acting on, then it pulls out a fixed number of subpixel loads, multiplies them by the filter, adds them up, rounds that down back to a single pixel value, clips it to the 0 to 255 range, and slaps it into the destination array. Okay, you know, that was a lot of code, but it was relatively straightforward. Let's try the SIMD version. It looks slightly more verbose because instead of like plus, you have to write Wasm I32X4 add. But that's not too bad. It's okay to be verbose as long as you're clear. Now, this does mostly the same things, but it operates on 4 pixels simultaneously, which gives it a noticeable speed bump. I was only able to use 4 lanes because the intermediate values in this particular algorithm are too large to store in 16-bit or 8-bit values. But when you can use smaller lanes, you always want to, because you'll get a direct linear speed up. If you can work with 16-bit lanes instead of 32-bit, it will go literally twice as fast. So first we load up 16 adjacent pixels. We don't actually need 16 pixels, but that's okay. It's easier to do this at the moment using 16 pixels because we're then going to take half of that and do a widening operation. So we widen the source pixels from 8 pixels to 16, 8 pixels? No, 8 bits to 16 bits, and then again from 16 bits to 32 bits so that we can operate on them. Then we take the filter, turn it into a vector, multiply, add, pretty much the same as we did in the scalar version. Where things diverge a little bit, oh no, that was the same. Where things diverge a little bit is in the rounding and the narrowing. You may notice that there is a narrow operation, but there is not a clip operation. There's no comparison, there's no minimum or maximum, because it turns out we don't actually need to manually clip the value because saturation is built into the narrowing operation. So I can just take a value that might be 256 or 257 instead of 255 and just throw it in there and say, you know, widen this back down to 16 and then down to 8 bits. And it says, oh, too big for 8 bits. You got 255. So that alone also removes a couple of operations, which is pretty nice. Now, we can actually reduce probably a couple more operations in the future using fused narrow and store instructions and fused load and widen instructions. But I believe these are still unimplemented. It is an interesting thing that Wasm SIMD is very much a work in progress. So if there is an instruction that you find you really wish you had, let people know about it. It may be possible still to add it. Now, changing just this filter function and another similar one increased the VP9 decoding performance by about 15%. 15% doesn't sound like a lot, but for 2 functions, that's pretty good. For AV1 decoding using the David codec library, excuse me, I've done a lot more SIMD work, and I get about a 90% speed improvement, which is nearly a doubling. And I expect to be able to get somewhat more once I do some additional work on it. A doubling in speed means you can bump up a full resolution level from, say, 360p to 480p or 720p to 1080p, which gives you a much sharper image. So you want that if you can. Now, for comparison, there we go. We're going to try some AV1 playback on the oldest browser and the newest browser. And you're going to see a slight difference in performance. So here's Internet Explorer running JavaScript build of the AV1 decoder at, what is this, 180p resolution. It's going to look not great. It's also going to take a long time to load. So you can see this is really choppy during the initial load as it's compiling everything. And then eventually it sort of smooths out. But if we go over to Chrome, there we go. We are using the SIMD and threading build, and we are going to pump it all the way up to 1080p. And it is totally smooth. So if you count the number of pixels that are being processed in 180p versus 1080p, you get a performance differential of something like 36 times. That's a pretty big improvement for several years of improvements on a system. So I'm pretty happy with that, and I'm very much looking forward to WebAssembly threading and SIMD both landing in all browsers. It's going to be pretty much fantastic for anybody doing image processing or video processing, anything where you have a lot of pixels to push through. It just is pretty freaking fantastic. Now I have to find my browser again. There we go. Now, a couple of gotchas. The biggest gotcha right now is that you have a combinatorial explosion of build options. Now, you already have to worry about JavaScript builds versus WebAssembly builds if you need compatibility with certain browsers that don't have JavaScript. That includes not just Internet Explorer, but also older versions of some browsers or current browsers on obscure platforms where they just don't have a WebAssembly build available, etc. And now we're adding in threading and SIMD. So currently, in experimental builds, I produce a JavaScript build, a WebAssembly build, a threaded build, a SIMD build, and a threaded SIMD build. This is kind of ridiculous. There's a huge proliferation of build scripts in my code base, and then I have to ship them all, theoretically. So I really don't want to do that. So I'm really looking forward to conditional sections and conditional compilation of some sort, where you can isolate some of those things like the SIMD functions in one section and say, okay, load up these functions if you have SIMD. And if you don't, load up the other functions and just use those. That's pretty much what native systems do. You can load up any code you want, and you just don't run the code that is problematic. Now, a few takeaways. So threading is available now in Chrome. SIMD is available behind a testing flag. Threading should be coming to Firefox very soon. We'll see about other browsers. I'm still hoping for soon. And it's relatively easy to implement as a developer if you have an existing code base that uses pthreads in emscripten. I'm not sure what the current state of things on Rust is. I will have to look it up. I'm suddenly very curious now. And the best case, depending on your algorithm and your code base, is that you might be able to scale linearly with the number of cores, which is pretty cool. And with SIMD, of course, it's not fully available in production yet, but you really should start testing now if you are on a project that could benefit from it. Sometimes auto-vectorization works, but a lot of times it does not. So try it out, see what it does on your code base. And if you have to write Wasm-specific code, by all means do. All the intrinsics are there. The headers are there. It's not too hard to put together. You can do conditional compilation in your source code, so you only have to do a couple of builds, but you don't have to have separate source files. And it can produce really huge speed-ups on specific algorithms. Your total runtime may not benefit as much, but if you spend a lot of time pushing pixels, hey, that's perfect. So that's about all I got. Thank you very much.